Hello, my name is Jacob Marks. In this presentation, I'm going to be talking about differential energy profiling, energy optimization via diffing apps. First, I'm going to be talking about what is the problem that this paper is solving, namely battery limitations in smartphones. Second, how do they go about solving it? What's their implementation? How do they evaluate their implementation? And conclude talking about how successful their implementation was. What is the problem that's being addressed? The problem being addressed is battery limitations. Smartphones are getting more and more advanced, and the apps that are on them are using more energy, but the smartphone batteries haven't been catching up. The batteries are staying about the same length. So what can we actually do to solve this? Well, the best thing seems to be better optimized code. But how do we actually find what we need to optimize? So in this paper, the authors talk about diffing, or differential energy profiling. The goal of differential energy profiling is to automatically find similar code in different apps and compare the energy usage for that code. But the authors go above and beyond regular differential energy profiling. Their implementation, diffprof, not only does regular differential energy profiling, but it also shows ways in which the code can be optimized. But before we can do differential energy profiling, we need to find similar apps with identical tasks. So there are many different apps in the market that do very similar tasks, and the authors identified them into 8 different groups. They found ones, for example, like SoundCloud, Spotify, and Pandora, which all implement similar tasks while trying to play back music. Also things like Skype and Facebook Messenger all have similar types of conversation applications. This table shows some of the 8 different groups that they showed, all of them non-game apps because these would be too difficult to compare, and they showed the different energy drain of each of these apps. So as you can see, a lot of the apps have very different types of drains. Some of them, like the antivirus, is quite low, while others, like the messaging, are quite high. Each of these has a very different percentage of energy that's actually in the framework versus in the app itself. So the authors found that heavy usage of framework services leads to high percentage of app energy drain occurring in these shared services, up to over 90% of the app energy consumption. So this suggests that learning more efficient implementations of app functions by comparing their energy footprints not only is possible, but actually is a meaningful and practical approach. This table shows the comparison of the framework energy versus the app energy usage from a number of the different groups. So for each of the groups, you can see that the apps use very different amounts of energy, but for all of them, the framework energy usage is far higher than the app energy. So this shows that if we can change the framework calls that are being used, that's going to help the app tremendously. This table shows the comparison of different apps within each group. The bottom triangle shows the percentage of overlapping framework method calls, and the upper triangle boxes show the matched app tasks and percentage of all tasks. So when comparing these different apps, what the authors use is called E-Flask matching. And the goal is to find 2 different Erlenmeyer flask-shaped call trees. When finding these 2 similar call trees, they can compare which one is more efficient. So how do the authors actually implement this? Well, their implementation, diffprof, is built on top of an older implementation, eprof. It's about 5.7K lines of Java code, and all the traces are on phones collected with eprof and then processed with diffprof. The goal is to have developers write automated tests for 2 similar apps. So an author who's making a messaging app, for example, could take Skype and run tests with eprof collecting energy profiles, and then run tests with eprof on their own app collecting energy profiles. They will upload the energy profiles to diffprof and use the GUI to try and find similar Erlenmeyer flask-shaped call trees and find which parts of the call tree are using more energy. So from here, the authors went on to evaluate their setup. So as stated before, they had 8 different app groups. They picked 5 different apps from each group and 4 older versions of these apps. All the app tests are less than a minute long. They were all tested on a Nexus 6 phone with a modified version of Android 6.01. So they found 12 different energy optimizations in 9 popular apps. From the comparison here, you can see a bitmap.compress call in the Wish app and the Let Go app, but the percentage of total energy drain was very different between the two. And many similar optimizations were already found within different apps, and even different versions of the same app, like these 2 versions of Pandora with the TextView.setText call, one of which, the earlier version of Pandora, used a far greater amount of energy, so it was already addressed by the developers of Pandora in a later update. For the differing results, they found that the task overlap between similar apps was significant, ranging between 7% and 61%, with an average of 27%, 24%, 28%, and 17% for the 4 groups respectively. They examined 20% of the matched tasks manually, and they did not find any false positives. In this table, various buggy and inefficient tasks are showed. From a number of different apps, there are primary tasks that have a huge energy drain, and some of them take up a very large percentage of the total energy drain, like the 17.5% from Pandora, or this 40% of the energy drain for a view root impl.perform traversal in WhatsApp and TextNow. So this shows that there are some primary calls that are extremely buggy and should probably be avoided for many of these apps. Diffprof's effectiveness in finding energy optimizations stems from the large overlap of Android libraries used among competing Android apps and accurate source-level energy profiling. So Diffprof wouldn't have really been possible without all the tools that were available to the authors through Android. So Android has many different tools that allowed them to view the different calls within the apps without actually having access to the original source code. This allows them to compare any apps with any new apps that could be used. In their discussion, they discussed that they envisioned that Diffprof's approach can be extended to effectively compare source code level profiling measurements of software and broader domains beyond mobile, such as games, web frontends, and server backends. Now, many different implementations they purposely did not look at within this paper because they felt that many of the tasks didn't overlap or could not be compared. And I think it's likely that things such as games would also be very hard to compare. Diffprof is built on the shoulders of a lot of related work, including many other energy profilers like eProf. But Diffprof is unique because it helps show whether and how app source code can be restructured. In conclusion, smartphone batteries are not improving much, but apps are getting much more complicated and using much more energy. The solution for trying to fix this battery issue involves optimizing app source code directly. Many apps implement similar features, and it's likely that one will be better optimized than another. Diffprof can help developers identify which apps have a better solution than theirs, or whether theirs has a better solution, and then it can suggest how to solve different energy hotspot code segments. Thank you.